All right, welcome back. So now we shift gears a little bit, and we're going to talk about something called space complexity. Everything we've talked about so far, we've been worrying about time, about how fast algorithms run, what the runtime is. That's called time complexity. We've been analyzing the runtime of an algorithm as the size of the input increases. Now let's talk about what happens to the space that an algorithm takes up as the size of the input increases. So we can still use big O notation for the same thing, use the same formal syntax for describing what happens, but now we're going to focus on space, the amount of memory that's taken up. So there's some basic things we have to get out of the way. One is that obviously as n grows, if we're approaching infinity, the size of the input itself, which is n, is going to grow. So we're going to ignore that part. You might hear the term auxiliary space complexity if you do some research, if you read Wikipedia or something. That refers to the space required by the algorithm only, not including the space taken up by the inputs. That's what we're going to talk about. We care about the algorithm itself because our n is growing. That's the in big N or in big O. That's kind of the point. We're going to say that as n grows, we assume that the input n is going to grow. So let's not care about that space. Let's care about what repercussions that has inside the algorithm. So unless otherwise noted, when we talk about space complexity, technically we're talking about auxiliary space complexity. Hopefully that's not too scary, but basically it just means we're focusing on what happens inside the algorithm. So some basic rules of thumb. The first is that most primitives, things like booleans, numbers, undefined, null in JavaScript, are constant space. So it doesn't matter what the size of the input is. If the number is 1 or the number is 1,000, we can consider it constant space. It doesn't matter if a boolean is true or false, it takes up the same amount of space. Strings are a bit different because they require O of n space. So if n is the length of the string, if we have the input grows to 1,000 characters, well, that's a bad example. If it grows to 50 characters, the string takes up 50 times more space than a single character string. Same thing with reference types, arrays, and objects. So generally, we're talking about O of n, where n is the length of the array, or the number of keys for an object. There's not really a length technically, but so if the length of an array is 4, compared to another one that is 2, it takes up twice as much space as the shorter array. So let's take a look at an example. So here we're focusing on not time complexity, we're focusing on space complexity. So this function called sum, it takes an array and it just sums all the items in the array. So we have a variable total, starts at 0. Then we have a loop that goes from 0 to the end of the array, and we're just adding in the value of each item in the array to the total variable, and then we return it at the end. So again, space, not time, is what we're concerned about. So what are the things that take up space? Well, no matter what the array length is, we have one variable called total, one number. And then we're looping through, but we're not concerned about the time again. And then we have a second declaration inside the for loop, let I equal 0. So that's another number. And that's it for space. We're coming back to the total variable, we're adding into it, but that doesn't matter. That takes time, but the space is already there. So no matter what the size of the array is of n, or in this case ARR, as it grows, it might be 1,000 items, it might be 1,000,000 items, well, it might be 10 or 50 or 1,000. Let's start with simple. It doesn't have an impact on the space that's taken up because we only have these two variables and they exist no matter what. We're not adding new variables based off of the length. We're adding to the total variable, but we're not making a new variable. So that really just means we have constant space, O of 1 space. It's always the same, no matter the size of the input. Here's another one. So this is called double. It takes an array, and well, why don't I just copy this one and show you? So I've copied it in, and it's called double. I'll pass in an array of 1, 2, 3. What does it return to me? An array with 2 items. What am I saying? An array with the 3 items, the same length, but each one has been doubled. And what's important to note, it is making a new array. So it starts with making that new array, then it loops over the length of the first array, and then it multiplies each item and pushes that on to new array. And then it returns new array. So what does that mean for the space complexity of this? As the array length grows, as the input approaches infinity, Let's ignore the fact that JavaScript can't handle that. What happens to the space that this algorithm takes up in here? So yeah, we have this. We're going to make a new array no matter what every time. But that's not that significant when we consider this right here. We have this new array, and it's getting longer and longer and longer directly in proportion to the length of the input. So if the array is 10 items here, we're storing 10 items in a new array. If this is 50 items, we're storing 50 items here in a new array and returning that. So the space that's taken up is directly proportionate to n, to the input array. So n numbers, we get O of n space. So we don't need to care about things like this. Simplify it down just to the fuzziest level, which is O of n, rather than O of n plus 1 or something like that, or actually plus 2, because we also have this. Those don't matter. So I know it's a lot, and it's hard to understand right away, and it might not click. That's okay, though. We have some exercises, but I want to make it clear that you do not need to master this before we move on. I should just, the whole point is that I should have, in 10 sections from now, we'll have a couple solutions, and I want to be able to say, hey, the space complexity of this one is great, and the time complexity of this one is terrible. N squared time complexity, but constant space complexity or something. And you should hopefully be able to understand what I mean by that